Okay, thank you very much. I want to thank Wilson and Mauro for inviting me to such a nice conference to speak about some of the research we've been doing at the Universidad de los Andes in Bogota, Colombia. The main topic of this is superconductor ferromagnet structures. After doing our homework, we hopefully get to go to the beach and see the nice locations here in Natal. So some more motivation for you guys to stay a bit longer. So, so anyways, this is being also done in collaboration with Marco Aprilli from the Laboratoire de Physique des Solides, France, Marc Blamar from Cambridge University, and Yoshiteru Maeno from University of Kyoto at Japan. Let's see what some of the work I will present here has been already published in these two works. So if you want more details, you can certainly take a look on these two papers. The outline of my talk is, first I will talk about superconductivity and magnetism in SF heterostructures. Then I will go on with critical current and magnetization measurements of superconductor ferromagnet bilayer structures first, and then the same magnetization measurements in ferromagnet trilayer structures. Okay. I have not really discussed too much about the applications of this, but I will use a very nice introduction by Anna in terms of memory storage and superconducting spin devices. Anyways, what is the situation of superconductivity and magnetism in superconductor ferromagnet structures? Here we have, for example, a bilayer. And here you have the superconductor, you have the ferromagnet, and we have normal proximity effect. What does it mean? Some of the Cooper pairs from the superconductor penetrate into the ferromagnet, making a very thin layer of the ferromagnet superconducting, essentially. So depending on the exchange field of the ferromagnet or the polarization of the ferromagnet, this is, for example, if the exchange energy is large, the penetration, ferromagnetic penetration depth is very small, right? For example, cobalt will have a smaller ferromagnetic penetration depth as compared to nickel, right? Also, during this talk, I will only talk about singlet superconductivity induced in the ferromagnet. When you have, it's well known that when you have a magnetic inhomogeneity, basically you do have long-range triplet superconductivity. So in this case, superconductivity can penetrate into the ferromagnet as if was a normal metal, right? You would not see the ferromagnet. One last thing, remember that why is that the superconductor ferromagnetic coherence length, this depth of penetration of Cooper pairs is so small, it's because exchange field tends to break Cooper pairs, okay? However, superconductivity survives even for situations where the exchange field is much greater than the energy gap of the superconductor. Let's see how that is possible. This is just a brief introduction to this FFLO state. You have a Cooper pair, you have two spin in the opposite directions. When it enters the ferromagnet, there is an imbalance because this spin is pointing in the direction of the exchange field, and this other one is pointing in the opposite direction of the exchange field. So it's not going, the exchange field is not going to flip the spin, but it's going to create an debalance in the momentum. So you have the so-called FFLO state, which Cooper pairs have non-zero net momentum when they are inside the ferromagnet. This essentially produces oscillations in the superconducting order parameter into the ferromagnet, right? And I will not go much in detail about that, but there are many effects, interesting effects taking place here. And that includes that if you do this with different thicknesses of the ferromagnet, you will get an oscillatory behavior in the transition temperature depending on the thickness of the ferromagnet, okay? So this is being and going on for more than 16 years now. A lot of experiments have been done, but surprisingly, there is very few on magnetization measurements. So for example, I look in Google, I get around 18,000 different things related to superconductor ferromagnetic structures. However, when I look in the literature, what about magnetization measurements? That's hard to find. I only found this one in 2002 by Kobayashi, who was the pioneer who was working in magnetization measurements on these structures. Then I did my work as well. We published magnetization, and then recently the group of Elisa Zaitovich in Brazil, in Rio, and Ederlin and Chacon, they have been dealing with this kind of magnetization measurements in this structure. So I believe tomorrow there will be a talk about this work. So, but it's really, really difficult to find people working on this. Probably the reason is because the interpretation can be a bit tricky. Anyway, so what is the effect of critical current due to changes in magnetic state of ferromagnet? So here, this is not magnetization measurement, this critical current measurement. I will talk very fast about this because it's related to the magnetization measurement of the bilayer structure. So you have a ferromagnet, you have a superconductor, and different states of magnetic state of the ferromagnet. And interesting is the coercive fields when you have the domain walls. Here, you expect to have stray fields from the ferromagnet underneath. So we want to know what happens to the superconductivity in these different magnetic states. Indeed, the results are here. Here you have how you start for large, for example, for this large field, then you go down, change the field, and at coercive fields you have critical current drops in superconductivity, and then it returns back to normal and then goes back and so on and so on and so on. So also this has been confirmed in the so-called magnetoresistance measurements. I won't go much in detail, but in effect, you have an increase in magnetoresistance when the superconductor is very just almost completely superconducting, but not completely. So that's why I get this. What's the explanation? Basically, when you have thick cobalt layers, for example, thick ferromagnetic layers, you have block domain walls that point in the autoplane direction, okay? And these block domain walls would, these stray fields would induce vortices inside the structure. Indeed, here you have a cartoon of what's going on in this structure, and how do you explain the critical current measurements. Now, we know clearly that if we, in this experiment, we see that here, somehow, here, when you increase the field, the magnetic field, and you saturate the ferromagnet underneath, then essentially you make vortices go away, right? The vortices who penetrate, they are gone here. This is normal because you have a current across the sample, therefore you have a strong Lorentz force. But if you reduce this Lorentz force somehow, and you have magnetization measurements on bilayer structures, that means I'm not injecting currents from outside, then what happens? First, we have to have a reference sample. This is very important because without this, it's very difficult to interpret your results. A reference sample means you have niobium 25 nanometers, cobalt 3 nanometers, bilayer structure. An important thing is that the cobalt is extremely thin, right? So the domain walls will not lie out of plane, but will be in plane. So therefore, you don't have stray fields. You still have proximity effect, but not stray fields. So indeed, you have a normal response, magnetic response of a type 2 superconductor. Remember, all the magnetic field is being put in plane. So you have a Meissner effect, you have a HC1, then you start putting inside vortices, vortex creation, I call this phase. Then you go back, you have vortex spinning, and then again, you here on the other side, you have a vortex creation in the opposite direction, and then you will have vortex creation and annihilation, as you can see here in the most obvious example, right? This phase is very important for you to remember, what I'm going to show you right now, later on. So, what happens when you have magnetization measurements of a bilayer structure now with thick cobalt, right? Here you have 40 to 55 nanometers bilayer, and indeed, here you have a super, if you do two measurements, one above TC, which is the one in red, and one below TC, which is the one in blue, right? So what you do is you subtract these two signals the same way as Kobayashi did in his work. You subtract these two signals, and you essentially get only the response of the superconducting layer, right? So what you would expect is also this, you would expect this kind of thing. However, you get this kind of behavior. Here is just the response of the superconductor due to the presence of the ferromagnet, right? So indeed, this can be explained. Basically, if we start here, a large field, we have lots of vortices in the plane, and then we reduce the magnetic field, and here you have the coercive field of the ferromagnet, and you inject at a coercive field a lot of vortices in the arrow plane direction. There, this is fully penetrated by flux. Essentially, you have almost destroyed superconductivity, almost. And then you go back, and then little by little, these vortices, the other vortices in the other direction, but in plane, start entering the sample, and this eliminating these other vortices which are there. And then the process repeats when I finish the cycle. So indeed, these two results, the critical current, and this one makes sense, what is going on in these structures. For the next part of my talk, I will focus on these multi-layer structures. You have ferromagnet, superconductor, ferromagnet, and cobalt oxide. So I want you to remember two things which are very important. Is that now I know, because of previous experiments, that the domain walls can be the enemy or your friend. Depends what you want, right? So in this case, I don't want a stray field from the domain walls. I say, okay, let's get rid of those guys for the moment. And what I do is I have thin ferromagnetic layers, nickel, which I make sure all the magnetic states are within the plane. But it's important here is that I put niobium, very thin layer, 25 nanometers. And as you'll see, if you check the Ginzburg-Landau coherence length for this type of film, it's about 19 nanometers. That means that the diameter of vortex is about 38 nanometers. So it gets way inside the nickel layers. So if you can picture the vortex here, but it's a vortex who goes also inside, the screening currents are going inside, even the ferromagnets, okay? So basically, I'm trapping or squeezing vortices inside. Okay, this is also important for the people who are not very familiar with this type of thing. What I do is I put cobalt oxide here to pin a little bit the nickel. So when I apply the magnetic field, I can have parallel magnetization or anti-parallel magnetization depending on the applied field. So here you can see parallel or anti-parallel because you have a small kink here, which means that it's not being completely changed the polarity of magnetization. Anyways, what are the results? We have niobium, superconducting niobium here in blue. That's why I use the color blue, because it's lower temperature. And red when you have high temperature. High temperature, you have just the ferromagnetics, the signal from the ferromagnets. And at low temperature, you have the contribution for the superconductor. And you subtract these two signals, something strange. Well, the first time I thought this was weird. Change happens. This is the magnetic response of the superconductor with the ferromagnet next to it, but it's not like a magnetic response we would expect from a superconductor, right? So something is wrong. No, it's not. I mean, at first I thought something might be wrong with this. So I check. I mean, many experiments. I always got this. Many instruments, many labs, just to make sure everything was working. And let's keep getting this and this and this. And then I figure out a model to try to explain what was going on. Bear in mind one thing which is important. When you look closely here, you have here that here you have normal spinning, vortex spinning phase, right? But here you have, boom, a drop in the magnetization. And that means that at least half of the vortices are flipping around, right? And then you again you get large magnetization. So what's going on? I'm going to quickly explain in this simple model. This is the vortices who are inside this structure. You have essentially a magnetic field coming out from the vortex, a self-magnetic field. But this magnetic field is also acting into the ferromagnets, right? So you can calculate this magnetic field, and it will exert a torque on each electron in the ferromagnet beside the superconductor, and you calculate the energy associated with this situation. And you can also do a better calculation when you include the ferromagnetic coherence length, the thickness of the superconductor, and also you can have a ratio, compare what would be the energy for two different ferromagnets, the energy ratio, okay? So let's see if this is the case, if this is actually, so bear in mind one thing which is important. If the electrons, in the ferromagnets are feeling a torque, also by Newton we have that the vortices are also feeling a torque, right? Therefore, what's going on? If this is the case, I say, okay, if that is the case, let's do some mathematical manipulation, bling, and I got this. This means that, in fact, I have the traditional vortex spinning phase here, and here, right at when it's going to do the switch of one of the layers, then you have a drop in magnetization. That means that half of the vortices are down and half of the vortices are up, right? And then when I increase the field, then the rest of the vortices switch down, as you can see here, and then you can see you recover the rest. What's important here to notice is that indeed there is a vortex flipping effect due to the reversal of one of the ferromagnetic layers. So for the first time in the literature, you are able to flip the vortex orientation, actually modify the orientation of vortex. I know that has happened. Anna mentioned this about today, about Yamada, where he has done this with magnetic dots. But that's with magnetic dots. This is with superconducting vortices, right? However, okay, so this is just to compare normal hysteresis loop and this one. And the important thing is that indeed, the difference between these loops, traditional superconductors, in superconductors you have vortex spinning, vortex creation, vortex annihilation. Then in this one you have vortex spinning, vortex flipping, which is a new way to things, and then vortex creation. That means that vortex annihilation does not take place in this system, right? And that means that it's not dissipating energy in terms of form of heat, right? Maybe some interest. Anyways, I was wondering, this I actually made yesterday because I just wanted to have a look. How would it look like to have a vortex flipping effect occur in real life? I don't know. The answer is we don't know. We believe that when we flip this ferromagnet, maybe it's doing something like this, right? It is just a cartoon, but there is probably a lot of work for theoreticians to be doing how this vortex flipping may occur, right? What's important is that it is evidence that it's there. this is the last part of my talk. I replaced nickel with cobalt, okay? And the reason for this is that we wanted to see what was the effect of changing the ferromagnet. For this one has a larger exchange field, but has a lower penetration depth. That means that copper press penetrate less into the cobalt. And that means that the ratio of the energies are 0.4, okay? So that, in other words, the energy associated, the energy for doing vortex flipping, in a sense, is less than when using nickel. Okay? Indeed, the results did not show vortex flipping. Okay? So here you have the signal. Here you have the signal above TC, this solid line. And here you have the signal below TC, right? So nothing is, it looks like there's clearly not vortex flipping, a standard signal. However, this was surprising. There is a reduction in the coercive field of the ferromagnet, which was pinned. So this is parallel, anti-parallel, and then parallel again. So this ferromagnet F2, there is a reduction of the coercive field. So now the energy does not seem to be enough to flip the vortex, but is enough to alter the coercive field of the ferromagnet. Okay? That was very surprising, and it's so surprising that we just report this result, but we could not have a clear explanation what was going on here. So this is an open question on why the coercive field of the ferromagnet reduces when it's not able to flip vortex, but something is happening, right? So, anyways, I have 3 minutes. Okay, so this is before going into conclusions, this is like you have to pay some price for doing this kind of business, but the price is not to flip the complete vortex, but just to reduce the coercive field. So how is this happening? What's the mechanism inside? We analyze many possibilities, but we rule the field from the superconductor could not be, from the vortex could not be, so we are still, it's an open question. Anyways, what is the conclusions of this work? When you use nickel, you have the hysteresis loops are explained in terms of direct interaction of the superconducting vortices with the magnetic field of the ferromagnets, right? The field of the superconducting vortices with the electrons of the ferromagnets. This interaction is strong enough to be able to flip vortices, okay? Next, there is evidence of a novel mechanism of interaction between vortices and the ferromagnetic electrons. That is, this interaction is a consequence on proximity effect. That's very important. It's not stray fields, it's due to proximity effect. One way to differentiate between vortex spinning and vortex creation phases, okay, I didn't mention too much in detail, but you can look at the slope of the hysteresis loops, and then you can differentiate, okay, there's also vortex flipping or not. Anyways, when using cobalt, there is no observation of vortex flipping, and this effect is attributed that cobalt has a shorter coherence length, hence there is less energy for this process to take place. Of course, there is a reduction of about 400 oersted, which is quite large, of the pinning field. And the effect cannot be explained in terms of vortex fields, I already said that, but maybe it must be directly related to proximity effect. I believe it's a remarkable phenomenon that deserves further investigation. Thank you very much.
Okay.